is running. And start this.
So this morning I had a cup of tea. Today I've got a beer. Or tonight I've got a beer.
Welcome everyone. I see participants are trickling in, finding their seats. If you just caught what Larry said, he's got a beer. I hope you have some sort of drink too. I guess I don't have anything quite as exotic as that, but perhaps that's for tomorrow. We can try to escalate that and get some whiskey or something, you know, a cocktail mixer. Shake it up as we get started here. Welcome folks from, well, it looks like just kind of judging by the names here, it looks like we've mainly got people from the West Coast, which maybe, you know, maybe this was an easier time to show up, or also maybe you had a chance to see the keynote between the time of the first Q&A and the second Q&A. And so one thing that I've been trying, and it doesn't seem to have worked terribly well, is to ask people to submit questions beforehand. And so far we got one response, but the response was actually a question that I think the person then went and asked in the last Q&A. So I won't belabor that and cover the same ground again. But one thing I want to say is that Google form, which is linked below all of the plenary sessions, has a file upload option. So if you want to record a little MP3 or a little video, then please feel free to do that. That would be great. We could be nice to not just have two faces. We could have a third face temporarily, something along those lines. Let me just see. Okay, we're up to got a few more people here. And the way we're going to run this is we have this this Q&A option here, and I think I'll kick us off with a question, and then please type your questions into the Q&A, and then I'll sort of just read them out to Larry and take it from there. We try to keep it a little informal, as was, I think, very nicely wrapped up at the very end of the talk. It's a sort of a bit of a sharing experience, and the hope that we can kind of get insights from one another. So I thought I would start, Larry, by asking a question about the style of work that you do versus the style of work that I do. So I'm a professor, and you know, my output is really we write papers, which means we get them sort of just good enough to show the beginnings of an idea, and there's a long way to go before those things really make it to real robots. And that can be real robots in the sense of industry, or of course, you know, space exploration or rover applications. And I know that in some of the different funding agencies talk about this chasm of difficulty, of technical difficulty, of trying to get from what the academics do to these systems which are kind of ready. And I'm wondering, is there sort of a substantial overlap between the challenge that you face and say DARPA faces, or are they actually kind of orthogonal considerations? So like one of the things which came up a few times in your talk, and also in your question on your answers to questions, was about sort of radiation, which I assume is not that big a deal for most DARPA applications. So I'm just wondering about that, and also there's this question about the speed of the processes. So could you say a little bit about that challenge and maybe what's unique and maybe what's similar?
Sure. Okay. Well, there's several sub-questions there, so let me address a few of them. You know, at JPL, we don't have much access to basic research funding. So at universities, I think most of your funding is basic research. And there, you know, you're advancing to the body of knowledge. It's not necessarily tied to specific applications, although it, you know, it may address specific applications. At JPL, when we do research, it's much more frequently applied research where you have specific missions you're trying to enable. And that's especially true for the work we do for NASA, where NASA tends to lay out these long-term agendas where they know what science they want to do. And they work backwards from what is the science to what is the instrument that makes the measurement, to what is the spacecraft that carries the instrument, to what is the mission design. And so you've got this kind of really top-down, you know, work it out from the end goal backwards. What do I need? And it's very cost constrained. So you're always thinking, I mean, all of research is cost constrained, but here we're really filtering what gets funded by how we think it's going to impact missions down the road. So that's part of the answer. This chasm that you mentioned, we also have that. So there is funding, that is in NASA, or maybe it goes mainly to universities, but there's funding actually. So NASA has this scale they call technology readiness levels, which goes from 1 to 9, and basic research is down at the 2 or 3 end. And then 7 to 9 is when you're really building it to go to space. And there's this gap in between where it's kind of in the middle and maturing. And that's the valley of death, where you can get funding to take it to TRL3, and then it's hard to find funding to get it to TRL6. But once you get it to TRL6, then missions believe it's mature enough to actually use. So it's hard to bridge that valley of death. And then on the business about radiation, so we have this, in the robotics organization at JPL, a little bit of a disconnect that state-of-the-art algorithms generally tend to take a fair amount of compute, whereas what we can put in space tends to be pretty compute limited. So we have a, kind of another chasm there between, we're researchers, researchers like to push the state-of-the-art, and even at JPL, we like to write papers, and even at JPL, having your ideas out there and known is an important part, not of our performance review like a professor, but it's an important part of staying funded. So we got to write papers. But if you write papers,
there's an excellent paper in RSS this year by people at JPL. So certainly you guys don't only write papers, you write great papers.
So glad to hear that. Thank you. Anyway, so about the radiation business, there is research on rad-hard electronics. It's so far removed from what I do that I don't know what to say about it. But on the software side, we kind of just tend to take what's available. Or sometimes we get involved in research about software-based fault tolerance. So, how can you design the software to achieve the level of reliability in the face of a certain rate of bit flips, random bit flips. So I'm not sure if I've answered your question, but I've taken a shot.
Yeah, no, you absolutely have. And actually, one of the things I was expecting you to say was that perhaps the universities should get out of the ivory tower a little bit. But actually, that doesn't seem to be what you said. What you sort of said is more like there's an ecosystem, and and so everyone is working at the technology readiness level that where they can make a contribution. So we've got an excellent question here from Helen. So Helen, I was going to think about promoting you to ask you to say something, but you just added a postscript to say you're dialing in from Australia. So maybe I should take a stab of reading your question, unless you feel very strongly and would like to. If you would like to try that / trust me to figure out the technology to connect. So okay, so she hasn't replied. So I'll just read out her question. So she says, "Hi Larry, thanks so much for your awesome presentation. In your talk, you mentioned plans for some future lunar rovers and said that this is an opportunity to make rover development cheaper and more efficient. What are some of the most expensive and time-consuming areas of rover development that we should focus on first to make rovers cheaper and quicker to release into the real world?"
Excellent question. Not really an easy one to answer, but the mechanisms, all of the mechanical parts of rovers, maybe not surprisingly, cost more than the software and electronics. So we tend to be looking for, so then what drives the cost of the mechanism? And anecdotally, we think it's the touch work. It's still the labor that drives the cost of the mechanism. It's not the materials. It's generally the labor. So, and even in the labor, it may be generally in the testing, assembly and testing. It's not so much in the design. So you might think, more automated design tools would help. Yes, it would, but maybe that's not the dominant thing. If you can simplify the design so there's less parts to assemble, less parts to test, simpler. I mean, that's motherhood, but it's the truth. So.
And has the fact that you had this great picture with the different sizes of the rovers that have grown and grown and grown, and does making them larger, I mean, that makes them presumably just more capable, but is that also an artifact or a consequence of this, the labor involved, or has that scaled up? Or I would have imagined that perhaps the smaller rovers were harder to assemble, but perhaps not. Maybe they're simpler devices, so perhaps you can't compare them.
Well, the total mission cost has grown enormously from Sojourner to Perseverance, but so has the capability. And that growth has been driven by the capability that we wanted. So, based on the science that we needed to do, and therefore the instruments that we needed to carry, and the landing sites we needed to be able to access, that drove the cost. So.
And do you find, since you said the way that sort of the mission is, the whole system is sort of back-chained from what the science is going to be to, each of the requirements, do you ever find that they say, this is the science we'd like to do, and I could see you could say that's just not going to be feasible. We can't get a sensor of that sort. And conversely, are there some times when they say, yeah, we could do that, but by the way, we could add this other sensor for almost no cost, no payload cost or fuel cost or whatever it is, and it would allow you to do this other thing, which would be great. And so does that sort of back and forth ever happen?
Well, it does. And so now I'll explain a little bit about, there are different types of missions. So missions like Perseverance are what we call directed. NASA says, we're going to do this and we're going to give JPL the job. Then there are competed missions where, exactly like it sounds, NASA says, we're going to fund a mission where the total cost cannot exceed $500 million. And we'll evaluate proposals. And then you get into exactly what you just described. The scientists want to do something, and the engineers said, well, we'd love to, but we can't afford it. And I think, I'm not sure I can come up with an example right away, but certainly it happens. In fact, it's kind of did happen, in the MER rover mission that we launched in 2003. Prior to that, we'd been doing research on visual feature tracking for automated landing, but it was always a struggle to get funded. We had that chasm of death we were talking about. And then it turned out that mission realized they had a problem where they really needed a velocity estimate during descent. And it was a mission critical issue. And they came to us and said, can you do this? And we said, well, it's what happens. We've been working on kind of the pieces. So yeah, we think we can do that. And it saved the Spirit rover. So.
Yeah. Excellent. You would all, yeah. I wish I'd known that story, because I would have asked that question to get that answer if I had known that, but I didn't. That's great.
I had to slip it in there to make sure.
Well, so actually, one of the things I feel like is I've been asking some fairly general questions about sort of space and rovers, because it seems so exotic to me. But of course, your specific area of expertise is vision, right? And one of the things you mentioned was that in the previous Q&A is that when we were talking about hardware limitations, you were saying, one of the things is that, perhaps there's a prospect of in the future when you get other hardware, other computing hardware, you could run neural network-based techniques and so on. So could you tell me just a sort of a little more about your pet project, your favorite part of the vision pipeline? Or the part that you guys are most interested in the part that you're kind of most excited about? I mean, I noticed that you showed, for example, you had a few videos, but one was from the helicopter looking down, tracking those features. So I just thought I'd sort of ask you a bit more about what's going on there.
Like looking to the future, what is most exciting looking to the future?
Exactly.
Oh, that's a hard question. So speaking for me personally, what inspires me right now is the science that we're trying to enable. So my own personal research, yeah, it's great fun, but what really inspires me is what is the space science that we're trying to do? So, we are trying to help the scientists figure out if life ever arose on Mars. Or you kind of back it up, and so we don't know how to answer that, but more of this question of was early Mars habitable we need to understand better what was the climate. And so how can our robotics help inform those questions? And at that level, I don't really care what the robotics is. I care about the science. And now I want to figure out whatever is the right robotics to help those people answer that science.
Got it. I see.
That's what inspires me these days.
Yeah. Cool. All right, let's pause to see. I feel like in a class, I'm pausing to take any questions, and we have to give an awkward silence to see if we can get anyone to. Oh, not only that, but my office's lights are shutting down.
Oh my God!
I got to keep moving to keep the energy efficient.
That's funny.
Yeah, that's how they keep us on our feet. So let's see. So I was going to ask you a question a little bit about drifts. So you had an example in your talk where you said this is a drift. And at first I interpret the word drift as a verb. I thought, but I don't see anything moving. And I realized, oh, drift, you mean the sort of the geological formation of a drift.
Yeah.
And you said that's sort of a challenge. What is it about drifts that make them a challenge? And why are they still a challenge? Don't you have a spot in some of the Mojave Desert where you can simulate a drift and figure out those problems?
Well, I call them a drifts because when I call it a sand dune, the geologists beat me up and said they're not sand dunes, they're drifts. And it has to do with the size of the particle and how they form. And it turns out that there's almost nothing on Earth that is an exact replica of this particular style of pile of dirt, on Mars. So it's hard to find something that really looks like Martian drifts on Earth. And why is it still unsolved? Well, so why do we care? So the Opportunity rover got stuck in these things a couple times because it didn't have the intelligence to recognize when it was getting into one. And we didn't realize it was going to be a problem. So first time it happened, front wheels got buried, most of the way deep. And we spent 3 weeks doing testing in the lab back home to figure out, can we back out of this thing? So that can be a mission ender. And even if it's not a mission ender, sometimes there's these big fields of drifts and either you just can't go through them, so you have to go the long way around, or going through them, you have to only move like 10 meters a day. And so it's really painstaking. So there's a bunch of ways to address this. So if we have an image from orbit and we have really good localization, we could draw a path on Earth and say, follow that path, and it could do that. Or if we can do a better job of detecting them on board, then we can drive, in the gaps between the drifts. Or if we have some combination of better slip sensing or sinkage sensing, or maybe motor current, motor currents is maybe part of slip sensing, then we can tell, maybe there are small drifts we can actually drive over. But we need a better model of the vehicle thermomechanics, basically, and better sensor feedback so we can understand how to drive through this stuff. And why haven't we done it yet? It hasn't been the top priority. We're funding constrained and priority constrained. And that vision problem, if you treat it as a vision problem, you could treat it as a different kind of problem, like a wheel current measuring problem. But if you treat it as a vision problem, it takes a lot of computing. And we haven't had really that much computing on board, but I think now we do. So we're at a stage where, we have the wherewithal that we could solve that problem.
I see. So this thing about computing has come up a bunch of times, and it's made me wonder, there's two things going on. So one is that there's the level of computing you have, and it has to be rad hardened and so on. And the other is that the project timelines are there. I mean, I started the previous session by saying, oh, the helicopter went from 2013 to on Mars in 2021. That's a really short period of time to do that, a remarkably short period of time. But so this is my question, which is that, there are these laws like Moore's law or things like this, where I can't tell you how fast my computer will be exactly 10 years from now, but I could make an informed guess. And so I'm wondering, do you guys ever have projects where at the inception time, actually you don't have that compute available, but you're kind of pretty sure it will show up by the time you need it? Does that happen, or is that just sort of too much of a gamble?
Well, I think the answer is a little bit in the middle. So with that terrain relative navigation system, where we use the FPGA coprocessor to land safely, that's something where we could see quite a few years ago that we need that capability. But we could also see that it was probably going to be possible if we developed this board. So we start working on that. And then there was some back and forth. So picking a landing site for a mission like this turns out to be a very big production all by itself. We had a series of 4 workshops over, I'm not sure how many years, probably two or 3 years. And you start off with a dozen or more candidate sites and you narrow it down. And then you find out that the best site really needs that capability. So then you go see, how are we doing on the development? Okay, we think it's ready. So, okay, we'll go to the best site.
Oh, interesting. Okay. Oh, I hadn't kind of realized that actually the technologies were so site specific.
Well, they aren't all, but that particular technology let us get into much more dangerous sites. So, if we'd picked a site that wasn't very dangerous, we wouldn't have used it. We saved some money, but in this case, we had to have it. So, in my experience, there have been a number of times where technology I was developing got used in flight because the mission suddenly realized they had to have it. And if that hadn't happened, it would have just stayed on the shelf for who knows how much longer. But I, happened to be in the right place at the right time, or, maybe I made a good judgment call somewhere along the way and put myself, I think of research as kind of a game of probabilities. You're trying to maximize the probability that you're going to have some impact. So.
Yeah, except, well, impact in the good sense, not.
That's right.
Cratering into the planet. Yeah.
Yeah.
Well, there's some probability that's going to happen, I guess, and you guys you have a number on that, I guess.
0.5%, actually, yes.
That's actually surprisingly high.
Yeah.
It's a risky endeavor. Interesting.
Yeah.
So one of the things that I'm curious about is we have not had a big discussion where we've spoken a lot about kind of compute, but not a lot about sort of data availability. And of course, you've showed these great visuals of places where you kind of stitch together satellite imagery, remote sensing, and those things. If we were to go to a point where some stages into the future, you had far more compute, maybe you had sort of reconfigurable hardware like an FPGA, or you had some some device which is, let's say, runs a neural network. Of course, there's still the question of how you're going to train that thing, and how you're going to get training data. Are you going to get training data back? Surely you're not going to do the training there, or how do people envision that, or is that sort of too speculative to have any real sense?
Well, that's a great question too, and I'm not sure that I have a great answer, but we can talk about it a little bit. So one approach is if you have reasonably high fidelity simulation. So I think we all understand that simulation isn't the whole answer, but it gets you part of the way. And then you do have, by now we've had a number of past missions, so we do have some data. So then you can cross-train from simulation on the data set you do have. And then, you can do a little bit of it's not exactly on the fly training, but as you get new training data in situ, you can be fine-tuning your weights with the data you collect as you go. So it's kind of that progression from simulation to smaller data sets of prior data to fine-tuning on the new data.
I see. And so, I mean, because, for example, the previous rovers, lasted many years. I mean, I'm imagining that there was sort of a recalibration phases that were occurring, perhaps not continually, but periodically, right? So there is a sense in which, already in those phases there was some learning, or am I off base about that?
Well, since we weren't using neural networks, it was learning in a different sense. But yeah, we did have to try to update camera calibration models a little bit, for example, and there may have been other examples I'm less familiar with, but that is one that we did have to do. Yeah, or the arm sags. So there's probably some stuff that had to be done to update models of the arm and hand-eye calibration. So
interesting. And what about not so much? So what you spoke quite a bit about models of risk, and they seem to be about models of risk maybe there's the landing site question about the helicopter and navigation for the rover, but you have these different technologies at different levels of maturity, right? Some of them are technology demonstrations, and some of them are not. Some of them are really the robust platform. But is the rover, or when people think about designing the rover, is there a sense about which parts are going to fail and how? I'm imagining, like happened, that there might be some failures, but it doesn't debilitate the whole device. So you lose some wheels, but you find some various ways to carry on. I think of that scene in Terminator 2, or maybe it's Terminator 1, where the robot loses a limb, but it carries on and carries on and carries on, and I don't see very much of that in academic research. But when you've sent it all the way to Mars, you're going to try to squeeze as much juice out of that lemon as you can, I guess. And so I'm wondering, does it form the design phase a little bit, or is it just sort of like whatever happens, and then we kind of, back at ground control, we put our thinking caps on and see what else we can do?
No, it does inform the design phase. So we do consider failure modes and opportunities for redundancy. And sometimes with, particularly important components, we will have dual string, like we might have a dual string processor, or if there's a critical sensor, we'll have redundancy in critical sensors. Talking about wheels, I think the Spirit rover had one wheel fail. And so it was kind of, since it had 6, it was dragging one for the last part of its mission. Yeah. Or maybe it was a steering actuator, I don't remember which. So that is a design consideration. You can't protect against everything, but we do design in ways to be resilient in the face of faults. A particularly good example, maybe this isn't quite what you were getting at, but there's this thing we call safing mode. So if there's some upset on the spacecraft, it goes into safing mode, particularly during interplanetary cruise. Let's say there's some electrical event. The spacecraft goes into a mode where it's not going to do anything that kills it while we're trying to get back in touch.
I see. So it's hunker down and wait.
Yeah.
I see.
So suppose it loses its attitude estimate. There's this whole process where, that uses the star tracker to kind of, search for things it knows where to find and reestablish its attitude estimate.
It sounds like a phrase one should say to one's teenage son. You've lost your attitude estimate. You need to regain that. Anyway, so on that light note, I just wanted to say again, thank you so much for agreeing to, first of all, go through the rigmarole of recording the video and letting us sort of have that content and stream it and keep it up online, and then making yourself available at these 2 different times. It's well, as you can see, it's been a pleasure to talk to you. It really has. So thank you so much.
Well, thank you for inviting me. It's been a pleasure for me, and thanks for being such a great host.
Thanks. And, thanks to everyone in the audience and the people who are watching us. I see we've got more participants on YouTube, so that's excellent. With that, I'm going to try to see if I can elegantly shut everything down.
All right. Bye-bye.
Bye.